Okay, welcome to the final video of this pure ODE series. We're going to look at some applications of ODEs in the next series. But in this video, we're going to focus on how we find particular solutions of all of these differential equations that we have been looking at so far. So we're going to focus on non-homogeneous cases. So that is cases where there is a term which doesn't contain any y or y derivatives. And we're going to focus on the second order differential equation as well, although the theory could apply to higher as well. So what we've looked at so far in this series is that the general solution of this differential equation is broken down into two parts. So I'm going to call it YGS is equal to YCF plus YPI. Okay, so CF is the complementary function, and that is the part of the solution which, when you run it through the left-hand side of the equation, always will be 0, and that will contain all the arbitrary constants in the solution. And then the particular integral, that is the piece of the solution that, when you run it through the left-hand side, will always equal f of x. So when you add those two pieces together, then you will always get f of x. So this, therefore, is the general solution. Now, it's important to note that if this was a homogeneous case, i.e. f of x was 0 and that wasn't there, then the complementary function would be the general solution. However, the general solution when f of x is non-zero is not the complementary function. The most common mistake to finding particular solutions to these types of questions is to plug the conditions in too early and just plug them into the complementary function. You need to plug it into the general solution. You need both pieces of this puzzle before you can find the values for any arbitrary constants. Okay, so I've got 4 examples. I don't know how long it's going to take. It might be quite a long one, but let's crack on. So, first one. We're going to find the particular solution of this differential equation. This is a homogeneous one, which has a stationary point at 0, -2, and then we're also told to sketch the curve. So, jump straight, oh no, don't need a complementary function. Jump straight to the auxiliary equation, because the right hand side is 0, so there's no particular integral required for this one. So that's going to be 4 lambda squared minus 4 lambda plus 1 is 0, and that tells me that lambda is a half, or a half. Okay, so that's a repeated root, and you can get that by the factorising, quadratic formula, completing the square, calculator. Doesn't really matter how you get those two numbers. Once you've got the fact that we've got a repeated root, then we can jump straight to the general solution. In this case, x, because x is a function of t for this differential equation. So x is going to equal a plus b t e to the t on 2. Okay, so that is the general solution. Okay, call it the GS if you like, the general solution. We are now asked to find the particular solution, not the general solution, at such that it's got a stationary point at 0, -2. So this line here has 2 pieces of information within it, which is what we need because there are 2 arbitrary constants, so we need 2 pieces of information. The first piece of information is that the curve goes through the point 0, -2. And then the second piece of information is when x is 0, the gradient is 0, because it's got a stationary point. So let's use the fact that it goes through 0, -2 first. So to denote what I'm doing, I'm just going to pop 0, -2 over here on the left of my page. And that means when t is 0, x is -2. Just be careful because x this time is the dependent variable, so that's on the right. So that's going to give me that -2 is equal to a, because if t is 0, that disappears, and then that is the number 1. Okay, so I've got a value for a. Excellent. Right, I now need to differentiate this because my other condition is all to do with the stationary point. So I need x dot, or dx by dt, if you like. So I'm going to differentiate this using the product rule because I've got a product of 2 functions of t. So if I do this times the differential of this, that's just going to give me a b. And then I've got this times the differential of this, so that's going to times those by a half. So I've got a half a plus a half bt e to the t on 2. Okay. Now I can plug in my condition. And I also know that a is -2, so I can put that in as well. So stationary point, that means that x dot is 0 when t is 0. Okay, so that's the condition I'm putting in. X dot is 0 when t is 0. So x dot is 0 means I've got a 0 on the left hand side. T is 0. Again, that term's going to disappear. That term's the number 1. So I'm left with b plus a half a. But I know that a is -2. So that means I've got b minus 1 is 0. So therefore b must be 1. Excellent. I've now got numerical values for a and b. So I can state my particular solution, which in this case is going to be x is equal to, I'm going to write it as t minus 2 e to the t on 2. Okay, so that's going to be -2 in there for a. B is 1, so I've got -2 plus t. But to save me writing an extra plus sign, I swap them around. And then that's e to the t on 2. Okay, so that's my particular solution. This question also wants me to sketch the curve. So what I'm going to notice is that this is an exponential function with a positive coefficient of t, so it is an exponential growth. That's going to overpower the linear function as t tends to infinity. So I know it's going to look like an exponential going up towards infinity. I know that when x is 0, when t is 0, x is -2, because that was the condition. And I also know that was a stationary point, again, because that was the condition. So use that to your knowledge to sketch. And the only other thing I need to note is that, are there any roots? And in this case there are, because I have this linear factor here, and that will be 0 when t is 2. Okay. Typically, we would plot only for non-negative values of t. T usually means time in questions like this. So I'm just going to plot or sketch for non-negative t. So I know that -2 here is a point on my curve. I also know that's a stationary point on my curve, so it's going to come out horizontally from that point. And it had a root at 2, so let's just pop that here. And it's going to look like an exponentially increasing function. So its gradient is always going to be increasing. There's my t-axis, and there's my x-axis. Okay, there's my sketch. Of course, if you have a GDC, you could look to confirm that. So if I go into my graph mode in my GDC and I type the function, just be careful because this is a function of x in here. So I'm going to do x minus 2, and then I'm going to times that by e to the x divided by 2. Let's have a look at what that looks like. There we go. Okay, stationary point here on the y-axis. It cuts through 2 on my x-axis, and it's an exponentially increasing function. Okay, so you can use the GDC if you have one. Okay, right, so that was example number 1. Example number 2. Find the particular solution to this differential equation, which passes through 0, 0 and a half e. Okay, so first thing we need to do is write the auxiliary equation. Again, this is a homogeneous one because it equals 0, so we don't need the complementary function, particularly integral bit for this one. The auxiliary equation is going to be lambda squared minus 4 equal to 0, so that gives me two solutions. Lambda is plus or minus 2. Now, I know that we could use Shine and Cosh at this point, but we're not going to for this course, just because I'm focusing on what is expected in the MEI further maths course, and you wouldn't be expected to do Shine and Cosh at this point. We're just going to do E's. Okay, so now that we've got our two distinct real roots, we can state our general solution, which is y as a function of x in this case. So y is going to equal ae to the negative 2x plus be to the positive 2x. Okay, that is the general solution of my differential equation. Okay, and now to find my values for a and b such that this is true. So plug in these two conditions. Now the previous case, what in the mathematical world, what we would refer to as initial conditions, because the two conditions that were given were both to do with when t is 0, or when the independent variable was 0. we were given an x coordinate and an x dot coordinate when t was 0. So we call those initial conditions. We don't have that case here. We have two different values of x. Okay, two different values of our independent variable. So these are what we call boundary conditions. Slightly different in the way they work, but it's two conditions and it allows us to find the curve uniquely. Okay, but it means we don't have to differentiate this because it's 2 points on the curve as opposed to a point and a gradient. Okay. Right, so let's plug in 0, 0. So 0, 0. That's going to give me that 0 on the left-hand side is going to be a plus b. So i.e. a equals negative b. And then if I plug in the point a half e, that's going to give me e. Okay, y is e. Is equal to ae to the minus 1 plus be. Okay, so I've got a pair of simultaneous equations. Now, because of my e's that are kicking around in the second one, I'm not going to use the simultaneous equation solver on my calculator because questions like this are going to want exact answers. Okay, this is a pure paper. We like exact. So we're going to need an answer in terms of e. And the calculator won't give you a and b in terms of e. So we're going to have to solve it manually. So I know that a is minus b. So I can put that in. So I get minus b e to the minus 1 plus b e. So that's now an equation with b in it, only b in it. Times that equation by e, and then I can factorise out this b. So I'm going to get e squared is going to be equal to b into e squared minus 1. So that tells me that b is equal to e squared divided by e squared minus 1. Okay. Once I've got one of them, then I can plug it back into here. Where is it? There it is. To get a. Okay. So that tells me that a is equal to the negative of that, which I'm going to write as minus e squared over e squared minus 1. That will allow me to factorise out a load of e's from my general solution to get my particular solution. Okay, so now I've got values for a and b. Yeah, in terms of e, but they are exact. Okay, it is just a number. I'm going to plug those two back into here and give me my general solution. Okay, so therefore y is going to equal, and I'm going to pull out a factor of e squared divided by e squared minus 1. So that was negative one of those. And then I've got a positive one of those. Which, looking at that, I hope you can appreciate why there's kind of shines and coshes kicking around. Okay. All right, that is the answer. That is the particular solution. That is the only curve which satisfies the differential equation up here and passes through those two coordinates. Okay. All right. Example 3. A curve passes through the origin with a gradient of -3. So again, we've got another initial problem here. So the conditions that are given are initial conditions. Given that it satisfies this differential equation, find the equation of the curve. So we've now got a situation where the right-hand side is non-zero, i.e. we've got a term which contains no y's or any derivatives. So this is where we're going to need our particular integral and complementary function. So to find the complementary function, I'm going to jump to the auxiliary equation. So that's lambda squared plus 6 lambda plus 10 is equal to 0. So that's going to tell me that lambda is -3 plus or minus I. And again, you can either get that from the calculator or using the quadratic formula. This is a pair of complex conjugates. So my general solution, my complementary function is going to equal e to the -3x. Okay, y is a function of x, looking at the equation. So e to the real part times x into a times the cosine of the imaginary part, which is 1 times x, plus b times the sine of x. So at the beginning of the video I mentioned that a common mistake now is to use the conditions at this point. That won't work because this is the complementary function, not the general solution. You've got to put your conditions in the general solution. Okay, particular integral time. We've got a trig function on the right, and that means we're going to be trying ypi is equal to alpha sine plus beta cosine, which means ypi primed is going to be alpha cosine minus beta sine, and then ypi double primed is going to be minus alpha sine minus beta cosine. I'm going to take these three definitions and run them through. This will work, by the way, because I know there's an alpha sine here and there's a sine in my complementary function. However, the sine of the complementary function is actually multiplied by e to the negative 3x. So that is not part of my particular integral. So it does work. Okay, so second derivative. So I'm going to get minus alpha sine minus beta cosine. Then I've got plus 6 times the first derivative. So it's going to be plus 6 alpha cosine minus 6 beta sine. And then plus 10 times my function. 10 alpha sine plus 10 beta cosine. And I want that to always be equal to 39 sine. Okay. Equate the coefficients. So I've got a sine there, a sine there, a sine there, and a sine there. So that's 9 alpha minus 6 beta needs to be 39. And then the cosines, I've got one there, and one there, nothing on the right. So that's 9 beta plus 6 alpha. And that's going to equal 0. Okay, so GDC, we want equation solver. Simultaneous number 2. All right, so 9 alpha minus 6 beta is 39, and 6 alpha plus 9 beta is 0. And that gives me that alpha is 3 and beta is negative 2. Okay. Now that we've got those two values and we've got a complementary function, then I can state my general solution to this differential equation, which is y as a function of t. So y is going to equal e to the minus 3x into a times the cosine of x plus b times the sine of x. And then I've also got this, which, because it's now an answer, I'm going to write the full trig function. So that's 3 times the sine of x minus 2 times the cosine of x. Okay, so that's my general solution. All right, now I need the derivative because it passes through the origin with a gradient of negative 3. So let's differentiate that. So y primed is going to be, and a quick little product rule on this, the coefficient of cosine will be that times the differential of that, which is minus 3a, plus that times the differential of that, which is a b. So I'm going to get b subtract 3a times the cosine. And then the coefficient of sine is going to be that times the differential of that, which is negative 3b, plus that times the differential of that, which is negative a. So that's minus 3b plus a times sine. Okay. Then I've got the differential of that, which is 3 times the cosine, and the differential of that, which is going to be plus 2 times the sine. Okay. Right, now to plug in my conditions. It passes through the origin, which means that when x is 0, y is also 0. And that's going to give me 0 is equal to a minus 2. So that tells me that a is 2. And then the other condition was y primed is -3 when x is 0, because it passes through the origin with a gradient of -3. And that tells me that -3, okay, y primed, is going to be equal to b minus 3a. That disappears because it's a sine, plus 3. And that tells me that b is in fact 0. Okay, because a is 2. So I've got -3 equals 3 minus 6, which is true, plus b. So b is 0. All right, and then I can take those two and plug them back into this general solution to give me my particular solution. And I could, if I wanted, combine the two cosines. There we go. That is the only curve which satisfies a differential equation at the top and has a -3 gradient at the origin. Okay, I think we're doing well for time, 21 minutes in, and moving on to our fourth and final question. All right. So this time we've got z as a function of t. Okay, again, this is another non-homogeneous case because there is a term which contains only t's, and it's another boundary value problem because we've got 2 points that this curve goes through. Okay. So, complementary function. I'm going to jump to the auxiliary equation, which is lambda squared minus 2 lambda minus 3 is equal to 0. That tells me that lambda is 3 or -1. That means my complementary function is ZCF is equal to AE to the 3 t plus BE to the minus t. Okay, so that's me plugging in these two lambda values into that kind of general solution form for two distinct real roots. Okay, particular integral. So we're going to try z is equal to alpha e to the minus t, because that is what the right hand side of the equation. However, a constant times e to the minus t is already part of my complementary function. So that will fail. So that's no good. I can't use that. So when a particular integral is going to fail, then we multiply it by the independent variable and try again. So this time we're going to try z is equal to alpha t e to the minus t. And this one will work because that's not part of the complementary function. Okay, I need to take this trial form of my particular integral and I need to run it through my differential equation, which means I need the first and second derivatives of it. So I'm going to get z dot is equal to alpha into, and we're going to get this time the differential of this, which is just the 1, and then we've got this time the differential of this, which is minus t. And then z double dot is also going to be needed, which is going to be, let's do this time the differential of this, which is t minus 1, and then I've got this time the differential of this, which is minus 1, which can be written as alpha into t minus 2, e to the minus t. Okay, so there's my function, first and second derivatives. So I'm going to take those two definitions and plug them into here to get me a value for alpha. So that's going to be alpha into t minus 2 e to the minus t, minus 2 of the first derivative. So I'm going to get minus 2 alpha into 1 minus t e to the minus t, and then I've got minus 3 times the function, so it's minus 3 alpha t e to the minus t. And I want this to always be equal to 2e to the minus t. Okay, So what I should find is the coefficients of t cancel. Don't just assume that, actually check that, because that is worth checking, because it allows you to confirm that these are at least possibly correct. So we're going to get 1 alpha t over here, plus 2 alpha t from here, and then we've got minus 3 alpha t from here. So if I look at the coefficients of te to the minus t, that's going to be an alpha plus a 2 alpha minus a 3 alpha, which is always 0, which is good, because what we want, there's no te to the minus t on this side. And then finally the coefficients of e to the minus t, I'm going to get a minus 2 alpha from there and a minus 2 alpha from there, and I want that to always equal 2. So that tells me that alpha must be negative 1/2. So my general solution then is z is equal to my complementary function, which is ae to the 3t, plus, I'm going to write this as b minus 1/2 t into e to the minus t. Okay, so I've factorised part of the complementary function with the particular integral. Okay, it passes through 2 points. This is another boundary value problem. Okay, I've got 2 points that lie on my curve. So I'm going to plug each of those points in separately. So the first point at the top there is 0, 3/2. That means when t is 0, z is 3/2. So I get 1.5 is equal to a plus b. Okay, so a plus b is 1.5. Second coordinate I'm going to get is 1 and then 1 over e. That tells me that z is 1 over e when t is 1. So that's going to be ae cubed, and then I get plus b minus 1/2 e to the minus 1. Okay. So I'm looking at my notes over here, and I think I've made a mistake. Maybe. We'll go with it. Right, let's see what happens. Okay, so I want to solve these simultaneously. And I want them exact because I've got e's kicking around, so I can't use the calculator at this point. So I'm going to say that a is going to be equal to 3/2 minus b. So I'm going to get 1 over e equals 3 over 2 minus b e cubed plus b minus 1/2 e to the minus 1 times the whole thing by e, just to get rid of these two kind of fractions, and I'm going to put everything with a b on this side and everything without a b on the other side. So that's going to be a 1, because I've times the whole equation by e. I'm going to get a negative 3 over 2 e to the 4 from that term coming over, and I'm also going to get plus 1/2 from this term coming over, and then the coefficient of b is going to be the 1 from here, and then I've got a minus e to the 4 there. Okay. All right. So that tells me that b is going to be 3/2 into 1 minus e to the 4 divided by 1 minus e to the 4. Okay, so 3/2 is 1 plus 1/2 is 3/2 minus the 3/2 e to the 4, so that factorises out, and that actually cancels with this. So those two disappear, and I'm left with 3/2. And now I've got b is 3/2, I can go back up to this equation up the top here to say that a is 3/2 minus 3/2, so therefore a is 0. Now I've got a and b, I can state my particular solution, which is z is equal to a e to the 3t, but a was 0, so that actually disappears, plus b, which was 3/2, and then minus a half t e to the minus t. So that's the particular solution. I am going to factorise out a half, just because it will look a little bit nicer at the stage. So I get 3 minus t e to the minus t. Okay, so that is the particular solution to the differential equation. This question did also ask me to sketch the curve, labelling any intersections with the coordinate axes and any turning points. So what I'm going to do is differentiate this, because I need to find any turning points. So let's do this in a different colour. Z dot, which is z dz by dt, is going to be a half into this times the differential of this, so that minus is going to come down to give me a t minus 3, and I've also got plus that times the differential of that, which is a minus 1. So I'm going to get a half into t minus 4 e to the minus t. So this is going to have a turning point when t is 4, and that's the only turning point this curve has got. So t is 4 is my turning point coordinate. I know from my conditions it goes through 0, 3, 2 and 1 over e, and I can also see there's a root when t is 3. So root at t equals 3. That's a turning point there, that's a root there, and I've got 2 coordinates when t is 0 and t is 1. This is quite a small number, so about 0.4. So I can use all of that information to sketch my curve. Okay, so it goes through 0, 3, 2, up there. As t tends to negative infinity, this is going to shoot off to positive infinity. Oops, this one here. Because the exponential is going to dominate, and that's going to blow up as t gets really negative. So it's coming down from something really big. We know it goes through kind of 1 over e there. We know it's got a root at 3. So let's try and triple that distance a little bit. And then it's got a turning point at 4. So let's call that turning point there. And then also, as t tends to infinity, this whole thing is going to tend to 0, because again, this exponential is going to dominate. So the curve is going to end up looking something like, those points don't line up. It's going to end up looking something. Oh, that was a bad sketch. Let's try that again. It's coming down here. And then it's going to approach the t-axis. Okay, so we've got a horizontal asymptote there. At this point here is when t is 4. That's the turning point. That point there is when t is 3. That point there was 3/2 on my axis up there. That was my initial, one of my boundary conditions. And the coordinate of this is when t is 4. And when t is 4, I'm going to get half times -1, so it's -1/2 is e to the -4. So the coordinate of this is 4, and then 1 over 2 times e to the -4. Okay, so something incredibly small. And again, you can use the GDC to sketch that one. So if you go into graph mode, if you have a GDC, then we can sketch this curve, which was 1/2 times 3 minus x times e to the power of minus x. Might need to change the V window. 5 minus 1 to 2. Yeah, I mean, you still can't quite see where the turning point is. If you do G-solve, and you can look for roots, it will tell you that 3 is a root. And if you do G-solve again and look for the minimum, then it will tell you that t is 4 is the min, and that's the y coordinate of that point. So you can use that to sketch if you have one. All right. Thank you very much for watching. And that finishes this kind of pure differential equation series. And the last little bit of this further maths course is applied differential equations. So simple harmonic motion and systems of differential equations. Thanks so much for watching. Any questions you've got, please drop them in the comments below. And please check out other videos on my channel for help with your math studies.